Record started, sir.
Okay, okay, thank you. So as I said, probability and statistics is an important prerequisite for machine learning. So today, this afternoon, we will continue with probability and statistics. So we'll see how this is applicable in machine learning. Okay. I'll just take some real examples also. Okay, I may take some one or two examples. Okay. So where we apply probability and statistics in what you call say for example studying the population. Okay, study of population. That is, if you take say say some species of animal. Okay, for example, say a tiger or a lion. Okay, so you see that some species of animals are endangered. Okay, their population is endangered. Endangered means so their population will be declining. Okay, over a period of time, and as a result, what will happen is as say 50 years to go or some say 100 years to go, so this population will totally become extinct. So all the animals in that particular species will die. Okay, and then that species is totally extinct from the face of the earth. Actually, it means that you cannot find that species again on the face of the, like what you said, dinosaurs. We don't have dinosaurs now because they are extinct. Okay, but similarly, so there are so many species of birds, animals which are on the endangered zone. Actually, their population is declining, and you see that our the wildlife conservation, they take a lot of measures in say um, protecting that population. Okay, so something like that. So we have so a lot of applications like that, so where you can use this probability. Okay, so we will see that. Okay, we will see that um, in today's thing. But first, what we'll do is we'll get into uh, the basics of probability. That is, we'll take the first introduction of probability. I think this many of you may know that, but still, it is time. It's worth to go through that. Okay, so we'll go through uh, just the primer. So we'll just go through the what you call some slides. Okay, so which will discuss the basics of probability. Okay, so here we go. So here you see that generally we use when you apply probability, we generally apply something on a Markov chain model. Okay, this term may seem new to you, but this is actually a practical application. Okay, of some typical process. Actually, Markov chain is a process. Okay, so that means the occurrence, what is the Markov chain, is that Markov chain is an occurrence, for example, some event occurs, okay, today. So the occurrence of this event I, okay, will depend upon the occurrence of the previous event, I minus 1. So what is this Markov chain? Is generally a probability, okay, of of an event I given event I minus 1. Okay, event I minus 1. So this is conditional probability. Uh, so as I increments, so you know that the event at I depends upon the previous event. Okay, so like that. So that is what is called a Markov process. Okay, and this Markov process is very much applicable in many applications. Okay, so a lot of applications are there, so where we apply this Markov process. So this is actually one place where we apply Markov process. Okay, So that is actually basically probability. That is not probability because it's the probability of an event I given event I minus 1. Okay. So we'll go through that. Okay. And of course, we also need to have some idea about matrix because we'll be in Markov chain, we'll be using both probability and matrix. The matrix where the elements of the matrix are probabilities. Okay, so that's what actually. Now, when it comes to what is the probability? Okay, so when it comes to a probability, say that event is not certain to occur. Okay, generally we will see that some event. We'll here in probability we'll talk about event. Okay. So we talk about events. So we'll say that some events occur or don't occur. Okay. So if example, and what is probability? Probability is something that is indeterministic. Okay. If something is deterministic, then we say that the event will occur or not occur. Okay. Then you say you're deterministic about it. Okay. Like for example, you know that every morning the sun will rise on the east. Okay. So that you are very, very deterministic. That will not never change. Okay. But the sun will set in the west. That is also deterministic. Okay. So when you say that, so the rising of the sun. So the rising of the sun is a probability. Okay. So you can see that that particular event, the sunrise, okay, sunrise, okay, on the east, okay, is one. So because that is bound to happen. Okay. But the sunset, let the sunrise be event 1 and let sunset be event 2. That sunset will occur on the west is also 1. But if you ask me whether the sunrise will occur on the west, then for that, that will be 0. Probability of event 3, that is a sun will rise on the west. So that is equal to 0. Okay. So these are deterministic events. Okay. They are deterministic. So either they will occur or not occur. Okay. So these are such events are called deterministic. But sometimes what happens, there are some events which may which may have some uncertainty in them. Okay. For example, whether it will rain or not. Okay. Today whether it will rain or not. Say you want to take an umbrella. Okay. Or you want to take your raincoat. Okay. You know that it is a rainy season, so you want to be prepared. So, but you want to know whether it will rain or not. If that information is known to you, then you will have convenience because you have to carry the umbrella or the raincoat. So the event that it will rain, okay, probability, okay, rain today. You cannot say it is definitely it is 1. Definitely you cannot say the rain will occur. Definitely you cannot say the rain will not occur. But that value will be some value between 0 and 1. So the probability that it will rain today will be a value which is 0 and between 0 and 1, inclusive of 0 and 1. It includes 0 and 1 also. Okay. So that means it may not rain, it may rain, or there is some vagueness or uncertainty. So this is what we say uncertainty. So uncertainty in the what you call the data. Okay, the uncertainty is the data. Okay, so this uncertainty is what we measure. So we know that uncertainty. We always talk about uncertain. Okay, uncertainty. So how do you measure uncertainty? We measure uncertainty using probability. That's all. Okay, probability is a measure of uncertainty. Okay, so it's a value between 0 and 1, both 0 and 1 inclusive. Okay, so when you say the probability is 0.5, you say that there's a 50% chance of raining or not raining. 0.5 is actually 1 is half of 1 is 0.5. So you say that the probability is of raining is 50%, not rain is also 50%. Now you have two things, whether it rain or not rain. Okay. So that is where the probability comes in. Okay. So we'll see like this. Okay. So here I have taken the example of 50% chance of germinating a seed. You take a seed, you sow the seed in the soil, you put water, okay. But what is the guarantee that this particular seed will germinate, will become a plant? Okay. So again, that you know that not all seeds are capable of germinating. Okay. So you will suppose you take I say half. The probability of germinating is half. That means if you put a seed in soil, so there's a 50% chance that that particular seed will become a plant or not, simply it will decay. Okay. So that's a 50% chance. Now, you can do that in that manner, look at that in that manner, or you can look at that in another manner. Say, for example, you take 100 seeds, okay, and you take 100 seeds, you sow them, okay. You take 100 seeds from a same sample, you take 100 seeds, you sow them, and you say that there's a 50% chance. So then what is the meaning is that out of this 100 seeds, approximately 50 seeds will become plant, germinate, and approximately another 50 will not germinate. That's the meaning. Okay. So that means there's a 50% of the, say, 100 seeds. Not now 50 means I don't say exactly 50. It will be something like, for example, 45 will germinate, or 55 may not germinate, or it may be 48 which may germinate and 52 may not germinate, or it may be 55 that may germinate, 45 may not germinate. So like that. So there is always some uncertainty, but approximately you can say that when the number of seeds is high, say when we take 100 seeds, then there will be a 50% chance will be something more or less, say, like what I said, say 45 to 55%. But if you take, say, more than that, say 1,000 or 10,000 seeds, in that case, what will happen? You will come to a closer figure. Okay. Similar to tossing a coin. If you toss a coin 10 times, so you may get say 6 heads and 4 tails. Okay, but actually it's a 50% chance. Suppose the coin is a fair coin. That case, tossing a coin will give you 50% chance of head and 50% chance of tail. But when you toss it 10 times, you may get a imbalanced figure like this. You may get 6 heads, 4 tails, or sometimes you may even get 3 heads and 7 tails. Okay, but when you do the experiment, when you toss the coin for, say, for example, 1,000 times, now your results will become more accurate. You will start to see that out of this 1,000, some 495 will be some heads, and the remaining 5, not 5, will be tails. Okay, so something like that. Okay, so the accuracy, that is the accuracy of the probability will, it's not accuracy of the probability, the probability will become more specific when the number of trials are increased. Okay, but when the number of trials are less, you may not get the exact 50-50. Okay, right. Okay, and next thing is, suppose you have a set of events. Okay, in a particular, you take a particular domain. In that domain, you have a set of events. So if you take the tossing a coin, so what are the 2 events? When a coin is tossed, you may get a head and you may get a tail. That's 2 things are possible. Only 2 things are possible. There's no other thing which is possible. Okay. So when you're tossing a coin, the what you call the universe is just 2 things. One is head, another one is tail. 2 events only. In that case, if one event has probability P, okay, for example, tossing a coin, okay, now I say the coin may not be fair. So if I say a fair coin, then fair coin means a coin which is perfect. In that case, the probability will be always 0.5 for head and 0.5 for tail. Okay. So total will be always 1. Okay. So total will be always 1. But sometimes the coin may not be fair. In that case, what will happen? The probability of head may be slightly higher. It may be 0.65 head and 0.35 for tail. So, in that case, when you add things up, what you get? You get 1. So, you have 1. So, 1. So, anyway, if the probability of an event, if there are two events, E1 and E2, in a particular problem, there are only two events, then probability of E1 is equal to, if you say it is equal to P, that probability of E2 will be 1 minus P. Okay, the probability of E2 will be 1 minus P. Since probability of E1 plus probability of E2 will be, okay. So that's the reason. Okay. So so if you know the probability of one thing, if there are two events, one probability of one is known, the probability of other is automatically known. Okay, because the sum of the probability cannot exceed 1. The probability can be a value between 0 and 1. So here I told the probability can have a value between 0 and 1. So that's what it is mentioned here. Okay. Now I will take an example of an ant. Okay, an ant. So an ant that is moving in a plane. Okay, for example, on a plane, an ant is moving. So you know the directions. Okay, the directions are north, then east, west, and south. Suppose an ant is here. This is an ant. Okay, and this ant is trying to move. Okay. So actually there are, I will add some more directions also. There are 8 directions. This is northeast, this is northwest, and this is southwest and southeast. Now suppose okay. Now suppose the ant. Now the ant can move in any one of the 8 directions. So there are 8 directions totally. Okay, it can move purely north, south, east, west, or it can move northeast or southeast or southwest or northwest. These are the directions in which it can move. Now there are 8 directions. Now suppose in absence of any other information, okay, so then what is the ant? We do not know, because the ant may take any direction as far as we know. But the ant may have made a decision to move in some direction, that we are not bothered. As an observer, you are observing the ant move. So the ant is not communicating to you that what is its intention. So when it starts moving, so you think that it will move in any one of the 8 directions. Okay. So then what is the probability? If you say that the probability of moving in any one of the 8 directions is equally probable, all are equally probable, then you will say that the probability of moving in any direction is 1 by 8. Okay. So it is 1 by 8. So ant moving in any one of the direction is 1 by 8. So ant moving south is 1 by 8, ant moving north is 1 by 8, ant moving east is 1 by 8, something like that. So there are 8 directions, and moving from one direction to other direction, say moving in a particular direction is 1 by 8 probability. Then there are 8 directions. If you add 8 1 by 8, 8 times if you add 1 by 8, what you will get? You will get 1. Okay, so the total probability is 1. Okay, now I will say the ant moving north. Okay, the ant is moving north. Probability that the ant is moving north. Probability of ant moving northward direction is 1 by 8. Okay, and the probability of ant moving south is also 1 by 8. Okay, but these two events, probability of moving towards north and probability of moving towards south, these two events, they cannot occur simultaneously. That you have to keep in mind. These two events cannot occur simultaneously because a single ant cannot move in both the directions. It can either move north or can move south. So such events are called mutually exclusive events. So we call them mutually exclusive events. Okay. So in that case, if you have I number of events, which are here, there are 8 number of events which are mutually exclusive, and can move in any direction, but all events are mutually exclusive. Okay, right? So this is what actually we mean by mutually exclusiveness. Okay, so an ant cannot move in two directions at the same time. So moving to north and moving to south are mutually exclusive. The events cannot occur at the same time. And we say that if two events E1 and E2 are mutually exclusive, they are mutually exclusive, then the probability of E1 or E2, because they cannot occur simultaneously, we cannot say and. It's not possible. We cannot say and. So we can say that because the events are mutually exclusive, any one will occur. Either E1 will occur or E2 will occur. In that case, the probability of E1 or E2 is that nothing but just the addition of the two probabilities. That's all. What is the probability of an ant moving north or an ant moving south? It is it's nothing but 1 by 8 for moving north plus another 1 by 8 for moving south, that is equal to 1 by 4. Okay. So the probability of moving either northward or southward is actually 1 by 4. Okay. So that is what you have to keep in mind about mutually exclusive events. Yeah, now we take the same problem, and now what we do is we just slightly modify this problem. Now you see that this diagram is there. Okay. Now we'll take yeah, I'll just write it here. Now what we'll do is we'll just take this diagram and just expand it. We take this diagram, and suppose now I say an ant moving northward. Northward means an ant can move not exactly north, but northward. Northward means it can move north, or it can move northwest, or it can move northeast. So this is called northward. Okay, northward means either anyway it can move east or west also, but it is the main direction is north. So it can move northward, means north, northwest or northeast. Okay, and I say an ant, probability of an ant, the same ant, moving westward. So that will include what are the things it will include for westward? West, then northwest, then southwest. Okay, so these are the two events. Now I will say this is event E1, this is event E2. E1 is the event that an ant is moving northward. E2 is an event that an ant is moving southward. Now tell me, are these two exclusive events? Are these two events, E1 and E2, are exclusive? Now E1 and E2 are not exclusive. Why they are not exclusive? Because you find that northward direction, you find north, northwest, northeast. South, westward direction, west, northwest, and southwest. So you see that this northwest is repeated in both the events. So there is a common direction between northward and westward. Okay. So when I say northward, it also includes northwest. When I say westward, it also includes northwest. So these are the two common things. So therefore, E1 and E2 cannot be mutually exclusive. E1 and E2 cannot be mutually exclusive. In that case, now how will you calculate the probability? Now I will say, what is the probability that the ant will move either northward or southward. Now I want, what is the probability that E1 or E2? Which means that the ant either moves northward or southward. Yes. So in that case, what will happen? You have to take the probability of all this. Is it not? You have just add the probability of all this. So 1 by 8. Sorry. 1 by 8 plus again 1 by 8 plus 1 by 8 for all these three. Okay. Then again you have to add for this 1 by 8 plus 1 by 8 plus 1 by 8. But what is happening? This northward is happening 2 times. So you are repeating 1 by 8 2 times. Okay. So what is that you have to do? You have to subtract 1 by 8 you have to subtract. Okay, because you are accounting for northwest in 2 times. Okay, so therefore you have to subtract 1 by. Okay, therefore I can just say what is the probability that two events, what is the probability that two events E1 and E2 can occur when they are not mutually exclusive, when E1 and E2 are not mutually exclusive, what is the probability, or what is the probability that E1 or E2 occur? In that case, it is probability of E1 plus probability of E2. But now what you have is minus probability of E1 intersection E2. The intersection E2 is the common thing. That's what I told you. So that you have to subtract. Okay. So this is the general formula for probability of E1 or E2. If E1 or E2, if they are mutually exclusive, E1 and E2 are mutually exclusive, then this term is empty. This is empty. If this is empty, then that's the previous formula. Okay, P of E1 plus P of E2. Okay, so this is what you have to keep in mind. Okay. Just a minute. I will. Bye. Okay. Okay. Now, so that's what I was mentioning here. So the same problem. So here you see the northwest is common. Okay. So therefore you are accounting for that 2 times. So you have to subtract that 1. Okay. So therefore it is there are 1 by 8 plus 1 by 8 plus 1 by 8. So that is 3 by 8. Again here also 1 by 8, 1 by 8, 1 by 8. That's 3 by 8. Then you have to subtract one thing, that is 1 by 8. So that is the total probability of either moving northward or westward. Okay. Right. Okay. If events are not mutually exclusive, then the probability of one or the other, we must subtract the probability of the overlap. Overlap is the intersection. Okay, that's what I was mentioning. Okay. So we have seen one important concept of a probability, that is mutually exclusive events. Okay. Next we move on to another important concept, that is independent events. Independent events. So what do you mean by independent events? Say again we take two events, E1 and E2. If occurrence of E1 does not affect E2, okay, there are two events that are going to occur. If occurrence of E1 does not affect E2 or vice versa. The occurrence of E2 does not affect E1. Okay. Then, sorry, does not affect E1. In that case, we say that E1 and E2 are independent events. Okay. Okay. Say, for example, you can take the events of, say, for example, what is the price of the petrol? Whether the cost of petrol, price of petrol will increase today or not. Okay, that is one event. Another event you can say, what is the probability that the match will be won by India or Australia, something like that. So now you see the connection. There's no connection between the cost of the petrol and whether India or Australia winning the match. Okay, so these two events are independent. You can say these two events are independent. Okay. Or you can take two events. Say, example, say the today match is today's match they are going to schedule at today's match they are going to schedule at, say, Calcutta, India Australia match, something like that. Now whether it will rain or not in Calcutta, whether it is going to rain or not. Okay. So in that case, you see that they are not independent events. For example, if it is going to rain in Calcutta, then the match is going to be delayed. Okay. So sometimes the match may become a draw. Okay. So in that case, you see that now these two events, E1 and E2, are related. Okay. They are not independent. They are dependent. Okay. That means it is dependent in one way. That is, whether the match will be played or not depends upon whether it is rain or not. So that's a dependence. Okay. So this is what is called dependence and independent event. Okay. Now here you see that here I have taken another example. Say, for example, you take two seeds, you put two seeds into the soil. Okay. Now the two seeds are two exclusive events. Okay, they are two different events. One seed is growing, another seed is also growing. Whether it will grow or not doesn't depend upon the distance. It doesn't depend between the seeds. Okay, what is the probability that seed 1 will grow will affect seed 2? There's no dependency. Okay, so in that case, such events are called independent, like the example I told you before. Okay, so when you do that, when you have independent events, then what you can do is you can always put a and. Okay, so when I say the probability of S1 and S2, okay, probability of S1 and S2. So here I will say, I think the probability of two events, okay, S1 and probability of S2, when S1 and S2 are independent. When S1 and S2 are independent, then we say probability of S1 and, now we come to the concept of and S2 occurring together. So these two events occurring together. What is the probability of S1 and S2 occurring together? That is nothing but just probability of S1 into probability of S2. So that is when two events S1 and S2 are independent. If S1 and S2 are independent, they are independent, then just take the product of the individual probabilities and just multiply them directly. So that will give you the probability of simultaneous occurrence of S1 and S2. Okay. Now here in this example, you can just take, I take two seeds, okay, I put them in soil, and I'll see whether what is the probability that first seed germinates and also the second seed also germinates. Second seed also germinates. Okay, that is both the seeds becoming plant. So in that case, what I will do is, you know that we are given that the probability of germination, that the probability that a seed will germinate is 1.3. 0.3 is 3 by 10. Okay. Probability of germination is 3 by 10. And similarly, this is also 3 by 10. But you know that whether seed 1 germinates or not does not affect S2. Similarly, whether seed S2 affects or germinates or not does not affect S1. So these two are different. Okay. Then in that case, then what happens? Just you can just what is the probability that both the seeds germinate? In that case, what you have to do? Just you have to multiply the probability. Then in that case, it becomes 3 by 10 into 3 by 10. Okay. So which is equal to 9 by 100. So which is 0.09. So that's what we get here. Okay. So that means there's only a 9% chance, okay, of both seeds germinating. Whereas individually, if you take one seed, there's a 30% chance of germinating, because you see here, there's a 30% chance of germinating if you take only one seed. But when you take two seeds and you say that both of them germinate, given that the 30% for one seed, the chance of germinating is 30%, then for both the seeds to germinate, the chance is only 9%. The chance they are drastically reduced. Okay. So this is what is called dependent and independent event. When events are independent, you can just multiply their individual probability. This is the case when they are independent. Okay. Now, what happens when the events are not independent? Okay, just like I told you about the match. Okay, it will depend upon the outcome of the match will depend upon whether it rains or not. Okay, so raining is one event. I can call E1 as an event that it is going to rain, and E2 as the event of the outcome of the match, cricket match. For example, the cricket match will, whether any India will win or Australia will win, or there is going to be a draw or something like that. So that depends upon whether it's going to rain or not. Okay. So in that case, this is called conditional probability. Conditional probability. What do you mean by to say that? What is the probability that India is going to win the match, given that it is not going to rain? You are saying that it's not going to rain. Okay. Then what is the probability that India will win? Or what is the probability that Australia will win if it is going to rain? Okay. So in that case, what we'll do is we apply something called a conditional probability, where we put this symbol, bar symbol. Okay. So a bar symbol indicates the dependence between the two events. Okay. Conditional dependence. So that means that conditional dependence means an event E1 or E2 depends on E2. That means, sorry, E1. That is a condition that what is the probability that E2 will occur if given that E1 is known. Okay, given that E1 is known. Okay, in that case, what is the probability of E2? So that is the conditional dependence. Okay. Now, this conditional dependence leads to what we call the joint distribution. Okay, so we'll talk about joint distribution later. We'll come to that. Okay. Now here, you see that probability. So probability of E1, E2 given E1 is equal to probability of E1, E2 and E1 divided by the probability of E1. Okay. So the one which is given comes as the denominator. Okay. And on the top numerator, you get the joint distribution. So this is the probability of joint distribution of both E1 and E2 to put together. Okay. That's why you put the AND. Okay. So conditional dependence of E2 on E1 is equal to joint distribution of E2 on E2 and E1 divided by E1. Okay. So this is what is called the conditional distribution. Okay. So the conditional distribution comes when the events are dependent or independent. Okay. So if you bring this side here, so what happens is that if you bring this term here, then it becomes probability of E2 and E1 is equal to probability of E2 given E1 into probability of E1. So what is this? You can see that this is a joint distribution, and this is a this distribution is independent distribution, and this is a conditional distribution. So you have a conditional distribution and a single distribution. So what is that you have that you can this is a joint probability, so not distribution. I'll come to distribution later. So this is a joint probability, and the joint probability is a probability and a conditional probability. So that means conditional probability into a probability. So that means a joint probability can be factored. Okay, we can factor. Suppose we have given a joint probability. The joint probability can be factored into two things. That is one conditional probability, another probability. Okay, so this is what actually you have to keep in mind, right? Okay. Generally, in base networks, in all base nets, so given a conditional probability, we always try to factor it into independent probability like this, conditional and this one. Okay, and you should also know there's a chain rule. There's also a chain rule for E2 on conditional probability. That means, say for example, probability that an event probability that suppose there's an event En that depends upon En minus 1, comma En minus 2, comma En minus 3, comma E2, E1. This is a conditional probability that an event En depends upon En minus 1, En minus 2, En minus 3 like that till E1. In that case, you can always put it in a conditional, you can always put it in a what you call we can have a chain rule. Okay, so I can always write it in a factored manner. I can always write it in a factored manner. Okay, sorry, not given here. Sorry, I'll say probability of E1. So this is a joint probability of n events. Okay, joint probability of n events, E1 and this means an E1, En and En minus 1 and En minus 2. So this can be written as probability of En given En minus 1, En minus 2 up to E2 En, sorry, E1 into what? Into into probability of okay, right? So this is how I can write. Now what you can do, you can apply chain rule to this one. Okay, that is probability of En minus 1. This can be this is again a joint probability that can be again factored as En minus 1 given En minus 2, comma En minus 3, E2, E1 into En minus 1. Sorry, probability of En minus 1. And already you have probability of En. Okay. So likewise, I can do this. Okay, I can do this. I can convert a joint probability into this probability, and the conditional probability gives you the arrow. It tells you the using this conditional probability, what we do, we create a Bayes network. Okay, so that we always do in machine learning. Okay, right. So here we have taken an example of our present situation. Say, for example, a person who is exposed to certain, say, COVID-19. Okay, a person is exposed to COVID-19 is quarantined. Okay, so we are taking 100 people. Okay, and we take 10%. 10% of that 100 are exposed. 10% of the 100 are exposed, and two of them have been two of the exposed have been quarantined. Okay, so this is the data given to you. Okay, that out of 100 people, 10 have been exposed to COVID-19, and out of it, 2 have been quarantined. Two exposed persons have been quarantined. Now, what is the probability? Now you can just calculate the probability. Okay, what is the probability that so total n equal to 100. Okay, number of exposed equal to 10, number of quarantined equal to 2. Now what you do in this 100%, you just randomly pick a person. Okay, randomly pick a person. What is the probability that he is exposed? Out of 100, 10 are exposed, 2 are quarantined. Now you randomly pick one person from this 100. What is the probability that he is exposed? Probability of he. Probability that he is exposed is equal to 10 by 100. So that's the probability, because you have the basically mathematically what does probability mean? That total outcomes divided by the favorable outcome. So this actually I forgot to tell you in the beginning. So probability is the ratio between favorable outcome divided by the total outcome. So the total outcome is 100% and 10% are exposed. So what is we want the probability of a person you are picking to be exposed. So that will be so 10% are exposed, that is favorable to you, and 100 are the total people. So 10 by 100, that is equal to 0.1. So 0.1 is the probability that a person you pick will be an exposed person. Okay. Now what is the probability that a person you pick is quarantined? What is the probability that a person you pick is quarantined? Now the number of person who is quarantined is 2, and the total number of person is 100. Favorable person is 100. Sorry, total count is 100 and favorable is 2. Okay, you randomly pick a person, and what is the probability that he is quarantined? Okay, that is equal to 0.02. Okay, now I want to have a probability. What is the probability that a person is exposed and quarantined? What is the probability that a person is exposed and quarantined? So that's what actually I think the problem is. Okay, this we know that 10%, and this is 0.02% chance of being occurred. However, if our selection is only for the subset 10 exposed people, then the probability of picking one of the two individuals. Yeah. Now, what is the probability of, this is also given, what is the probability of a person who is exposed and quarantined? So you know that number of persons exposed is 10, and the number of persons who is quarantined is 2. Okay, so it's only 2 by 10. The probability that a person is exposed and quarantined is 2 by 10. That's 0.2. Okay. Okay. Then the probability of picking 2 persons is also, that is 0.2. That's 20%. Okay. So the probability that a person is exposed and he is quarantined is actually this much. Point. Right? That is now what you have to do is you have to take both. Okay, you have to take, so you have to apply the formula. Okay, that is, sorry, what is that we want? Probability that a person we want to have the probability that a person is quarantined given that he is exposed. This is what we want. We want the probability that a person is quarantined, you are given that he is exposed. So that's what we mean here. The probability that a person, that an exposed individual is quarantined. Okay. So he is exposed. You know that he is exposed. Knowing that he is exposed, what is the probability that he is quarantined? That is equal to our formula, probability of E, sorry, okay, that is B. Just a minute. Yeah, E and Q divided by probability of E. Okay, so the probability of E is known here, 0.1. And what is the probability of the probability? Yeah, this 0.2, 0.02 is the chance of selecting an exposed person. Chance of selecting a person being quarantined and exposed. Okay, so 0.02 is the, yeah, this data we need. Okay, sorry, not this is exposed and quarantined. Yeah, this is exposed and quarantined is 0.02. This is, sorry, I made a mistake. A person who is exposed and quarantined is 0.02, so it's 0.02. So if you do this, this is 2 by 100 into divided by 1 by 10. That 1 by 10 will go up, so it will be 0, 0. That is 0.2. So I think I just gave you the answer. Okay, so without working out. Okay, so that what the probability that a person is quarantined given that he is exposed is 0.2. Okay, where 0.02 is the probability that a person is both exposed and quarantined, because when you are picking a person randomly, if the person is quarantined means he is exposed. Okay, so the probability, so 0.02 is the probability of P, probability of E and Q. Okay, probability of E and Q. This is probability of E and Q, and this is probability of E. Probability of E is 0.1. Okay, and so the probability of a person who is exposed is and quarantined is equal to the probability of E and Q divided by probability of E. That becomes 0.2. Okay. Now it's clear. Okay. Now what I will do is, before I come to this part, I will take another part. Okay, that another part is this one. This I will see. I'll come to this later. Yeah, I'll go here. Yeah. Now here I will come to a topic called distribution. Okay. So what we have seen so far is about some concepts in probability. Okay. And now we come to the concept of distribution. Okay. So probability and distribution, so together it makes meaning in our application. Okay. So why we need probability and distribution is because we are always interested in simulation. Okay. Simulation and modeling. Okay. So why we want to simulate or why we want to model? That's what our need. Why do you need to do simulation? Okay. So there are situations in which what you can do, you can never do something, experiment and find the result. It's always not possible. In some cases you can experiment and get the result, but sometimes doing an experiment itself will be an expensive task. Okay. For example, measuring the power of an atom bomb or a nuclear bomb, you want to measure how much power does a nuclear bomb will have, that you cannot do it experimentally and come to a result. Okay. Why? Because that doing that is dangerous. At the same time, doing that is very uh, expensive. Okay. Another one will be, say for example, say you are a technician on a windmill, of a windmill. Okay. You know the windmills are very tall structures. Okay. So you have to climb the windmill. Okay. And you want to be trained on what are the different types of problems that may occur in a windmill. So in that case, they are again experimenting with a in a live mode. Okay, taking a person up to the windmill, top of the windmill, and making him working windmill and asking him to do all the jobs. That is also dangerous. Right? Similarly, for a pilot also. Okay, say a pilot, say who's getting trained. Okay, and now that pilot actually wants to get trained in making takeoffs and landing in different airports, okay, at different times, for example, daytime, morning time, say afternoon, evening, say night, different times, and also different weather conditions. Sometimes rainy, during rainy season, how to go about landing or take off. Similarly, in mist, fog, when there is huge fog, and how to do that. Sometimes how to do that in a summer day on a shiny, on a clear sky. Clear sky will not be a problem. Okay. How to go about take off and landing in a windy day. For example, there's a wind. Okay. So these all these situations you cannot simulate. You cannot have it in real time for a pilot to get trained, because all these situations will never come together. Okay. So you can train him on during the daytime, you can train him during the night time. But when you want to train him on a weather, for example, on a rainy day, then you have to wait for the rain to come. Okay. Or you want the storm to come, or you want the winter to come. So that in that case, that may take a long time for training. So at the same time, training on a flight is expensive and also risky for the life. Okay. So in that case, you want to simulate on a simulator. You want to simulate on a simulator, but that simulation should look real. Should look real. And as you know that the weather conditions, light conditions, all these things are mostly probable conditions. They are not. They are based on probability. Whether it will rain or not, whether it will be a fog or not. So everything is based on probability. So in that case, simulations are in turn based on probability. Simulations are based on probability. Okay. So you have to bring in probability somewhere. So in your computer program, because you are going to simulate on a computer. So when you are simulating on a computer, you have to bring in this probability. Okay. You have to bring in this randomness. You have to bring in this uncertainty. Okay. This uncertainty should be simulated so that the pilot who is getting trained on a simulator will think that it is actually a real condition. Okay. But actually that is actually simulated with randomness. Okay. Because if you don't have randomness in a simulator, then the pilot will learn it easily, because you know that it's like watching a movie which you have already watched. You know what is going to happen next. Okay. So if you know, say if you watch a movie second time or third time, you know what is going to happen next. Okay. So similarly, that will happen if a computer program for a flight simulator is a deterministic program. In that case, the pilot will easily know what is going to come next. So he will be prepared. So that will not be a training for him. So what is that you have to do? You have to put in some uncertainty, some randomness in the program. Okay. And that's where our probability and randomness come into simulation. So simulation is a very important field where we can go about having randomness in a computer program. Okay. And that's what actually for this thing is. And we call such a thing as Monte Carlo simulation. Okay. Where you involve random numbers. Okay. So in any simulation where you involve random numbers, then we call it Monte Carlo simulation. And another thing is, the random number you can never generate, because random number happens only in our real life. You cannot have a computer program to generate a random number. That's not possible. Okay. You can never write a computer program to generate a pure random number. Okay. Say for example, you are looking. Say you are at a crossroad. You are standing in a signal, and you are watching the cars go by. Now you want to know that how many red color cars are crossing that particular signal. So that is a pure random number. And that is only possible only in a situation, a real life situation. But you cannot make a program do that. Why? Because programs are basically deterministic program. Because when you write a program, you know it is deterministic. Okay. Programs are deterministic. Therefore, how a deterministic program can generate a random number? Okay. But we do have techniques. We do have techniques wherein we use deterministic programs to generate random numbers, and therefore those random numbers are called pseudo random numbers. They are not called random numbers, they are called pseudo random numbers. Pseudo means false. They appear to be random, but they are not random. They are pseudo random numbers. Okay, so that's what the thing is, and we simulate using pseudo random numbers, and such simulations are called Monte Carlo simulations. Okay. Now suppose, so just I'll give a simple example. Okay. Say you have a function. So like this f is not known to you correctly. Okay. If this f is known to you correctly, then what I can do, I want to compute the area between this 0 to 2. 0 to 2, I want to compute the area under the curve. So the curve is f of x, and that f of x, if it is known to me, f of x is known to me, then I can compute the area under the curve. How will I compute the area under the curve? Just integrate f of x. So just I want to integrate f of x over dx from interval 0 to 2. Okay, because I want to 0 to 2. So that's what I have written here. Okay, just you have to integrate. Okay, but this is possible only when you know the f of x. If f of x is known to you. But suppose f of x is not known to you, it is not a regular function, or f of x may not be integrable. Okay, because not all functions are integrable. If f of x is not integrable, then what you do? Look what you do. So in that case, what you have to do is you have to go for simulation. Okay, you have to go for the simulation, and you have to bring in the element of chance. So how will you do that? That's shown here. So what you do is the same thing what you have here, we are putting here, and we are enclosing this within an area, within a bounding rectangle. The rectangle length and height, you know. The height of the rectangle is 1.5 and the length of the rectangle is 2. So that you know. So now you know the area of the rectangle. Area of the rectangle is 2 into 1.5. 3. That is area of the rectangle. Area of the rectangle is equal to 3. Some 3 units square. Okay. Now what I want, okay. Now what I want is, I want the area under the curve. Okay. I want the area under the curve. Okay. So what you have to do is, the area under the curve is the area of the rectangle minus this. Okay. So how will you do that now? Now here is where what I will do, I will generate two random numbers x and r, y. X I will generate between 0 to 2 and y I will generate between 0 to 1.5. I will generate two random numbers x and y, x between 0 and 2, y between 0 and 1.5, random, purely random. So that will be just putting a dot, randomly putting a dot. Okay, and suppose that you have put so many dots. Okay. Now, the number of dots, so what you have put, you know that. Okay, for example, suppose I have put say 1000 dots, 1000 dots, of which 700 dots happen to be below the function, because that I know, because which I know the extent value of this function, this value. I know the at that particular point what is the value of function that I know, because the function I can see the curve. I can, whether the dot is inside or outside, I can always count. So I can count all the dots which are inside and on the function. I can call and say that there are 700 dots that are on the function and below the function. Okay, and that means there are 300 dots which are outside, which are greater than the function. So in that case, now I know the number of dots which are inside the curve is 700, and the total number of dots is 1000. In that case, there are, what is the ratio of this? The ratio of this is, so 2 zeros goes there, so it's 0.7 or 7 by 10. Okay. Now what I do, so I will say that the area under the curve will be 70% of the rectangle, 70% of the rectangle. So that will give me, say, what is that? For example, here I have taken some other value. Here I have taken that 778 dots are inside or below, on and below the curve, and total number of dots is 1000. In that case, the ratio is the ratio is 7.7. Okay, so it will be, when you divide by 1000, it will be 0.778. So now that is equal to, the area under the curve is equal to 3. 3 is the area of the rectangle into that 0.778. So which is 2.334. Okay, so that means now you say that approximately I get an area. Okay, not by doing a direct analytical exercise of finding the integral, because integral I cannot find for this function. If I can find the integral, then no problem. You need not go for Monte Carlo simulation. You can directly do the integral and find the area. But in case you do not know the integral, you cannot find the integral. In that case, you have to go for Monte Carlo simulation. Right. Now, instead of, say, for example, now for this we got that 3. Now, instead of 1000 dots, if I had generated 10,000 dots, or say 1 lakh dots. Okay, in that case, out of it, now there is more probability that there may be some 8, 6, 9, some number of dots which are inside, under the curve. In that case, now my ratio becomes 0.869. No, sorry. Not 869. Sorry, how many is there? 1 lakh. 1 lakh means I have to put in, I have to put one more term. Okay. Say some 890, 8,000, not say 88,000. There are 1 lakh dots. Out of 1 lakh dots, 88,690 dots are inside the curve. Okay. In that case, now my result will be somewhat, say 1, 2, 3, 4, 5. It will be 0.8869. Okay. Now into 3. Now this has more accuracy, because here you see it was 0.778, but here it is 0.88. So the better accuracy. Okay. So the area under the curve will be more accurate. Okay. In this case, that means what? The when you involve an element of chance, or when you involve probability, the more number of exercise you do, the more number of exercise you do, the accuracy of your results are better. Okay, that's what the main thing about statistics. Okay, in statistics, the data whatever you analyze or whatever you use for your experiment should be big. You should have large data. Then only your conclusions or your findings will be accurate. Otherwise, it may not be accurate when you follow, say, random numbers. Okay. So the measure of quality is, yeah, now you say what is the measure of quality and other things, we say it is the standard deviation, okay, that you know, because uh, say for example here, we always say that measure of quality is the mean, okay, the average. Average is always taken as the measure of quality, okay. Say I do repeat an experiment 10 times, take the average, take the outcomes, divide by 10. So take the average. So average is the measure. You will always say average is the average is the measure. Okay. So now, but that average will not never be a spike like this. Only in case of a deterministic program will be a spike. Okay. So there will be a small spread. There will be always a small spread around this average. And this spread is called the variance. Variance of standard deviation sigma. Sigma is standard deviation and sigma square is variance. Okay, sigma square or standard. So this is the spread that tells you this tells you this standard deviation or sigma tells you the spread around the mean. This is mean mu. Okay, so you predict that the value is around the mean, but there is some uncertainty involved, that is the spread across the mean, that is measured using standard deviation. So that's what the standard deviation means. So standard deviation can be either plus or minus. You can see here. So here it is plus sigma, here it is minus sigma. So it can be both ways. Standard deviation can be positive, negative, but variance is square of standard deviation, so always positive. Variance is always positive, but whereas standard deviation is positive or negative. Okay. Now, so you know that there are now you always know what is 1 sigma, 2 sigma, 3 sigma. So that's defined. Okay. So 1 sigma is defined as say 68.3% is 1 sigma. And then 2 sigma is defined as 92% or something like that. So nowadays you see, in companies we talk about quality, you say 6 sigma. So 6 sigma will somewhere be in this line. So actually it is, I have not drawn the figure correctly, but if you draw the figure correctly, it will be something like this. So very, very small numbers will be here. There will be a large value here, then again very small numbers. So when I take 6 sigma and all, so the number of failures will be much, much less. Okay, so we call it 6 sigma. Sigma stands for standard deviation. Okay. So this is what actually our thing is. Okay. Right. So I will not get into this. So so this is algorithm to generate random number using a program. See, this is 2 steps. That's all. You initialize your R0 to some 10. Then R1 is 7 times R0 plus 1. So in terms of Rn is equal to 7 into Rn minus 1 plus 1. So nth random number is found using the R minus 1 random number. Okay. So this and mod 11. When I say mod 11, I can generate random numbers between 0 to 10. Because when you generate 11, 11 by 11 becomes, mod of 11 by 11 becomes 1. So this is not a random number. So when you use the modulus 11, so we can generate random numbers from 0 to 10. We can generate random numbers between 0 to 10. And where the first value is said to be the seed of the seed value. First value is said to be the seed value. And if you are using this method, it's called linear congruential method, and you are using the same seed value, then you will get the same sequence of number. The sequence of random numbers will be depend only on the seed value. If you give the same seed value, the same sequence will reoccur again and again. But for a given seed value, the sequence will be looking more or less random. Okay, right. So I think with this I need not spend much time here. Okay, right. Now I will get on to the next topic, that is about simulations using random numbers. Now I will talk about distribution. Okay, so you see that what we have talked about. We have talked about probability. Okay, so what I said is probability. Probability is the measure of uncertainty. Okay, then we brought in some method where how to include this uncertainty or probability in our computers, so that you can do through random numbers. Okay, by generating random numbers, simulating with random numbers. Okay, that we have done. Okay, so now for that matter we have generated pseudo random numbers. Okay, now having generated pseudo random numbers, now what are the various distribution? Now this is where we are again interested in. Why? What is this distribution? Why we should talk about distribution? Okay, so here you see that there are in real life there are so many distributions which are there. Like for example, I'll tell you. For example, when I talk about distributions, okay, I mean probability distributions. I don't mean distributions means probability. Probability distribution. So how this probability, these random numbers are going to be distributed. So because when I say probability, I mean random numbers. Okay. Now here I'll give you some real life scenarios. Okay, like for example, say I gave you already. You are standing in a signal, a crossroad, and you are looking at the car. Okay, and you want to count the number of cars, say of a particular brand. Say for example, say how many Volkswagen car they passed that signal. Okay, so number of, you want to count the, you want to have a, because that will be naturally a count. It will be a random count only, because you cannot say which car is what. Okay, so there are say 4 or 5 brands. If you take say Ford, India, if you take Tata, Ford, Maruti Suzuki, Kia, and so many. So there are around 10 brands. Okay, so out of these 10 brands, how say what is the probability that the next car that comes to the signal is a Ford car or it is a Volkswagen car? So that's a probability. And counting it, say for example, how many is coming in this 1 hour? In this 1 hour, how many cars of say particular brand is crossing? That is a pure probability value. It's a pure probability value, and it will follow certain distribution. It will follow a certain distribution. So, for example, here again another example I will give you, very easy example. Say you have a bank. Okay, so you may have a college. In your college, you may have a bank, and that bank has teller. You know teller. What is teller? Or ATM. Okay, automated teller machine. Say that has two ATMs. Now the the branch manager is getting complaint that there is a long queue. There is a long queue before the ATM, and the service time takes long time, because when a person who comes here, he wants to use the ATM, he has to wait for long time. Okay, and then he has to go inside and do his transaction. Okay, so there's a waiting time. Okay, in addition to the service time. So ATM services, service time of ATM may be say few minutes. Say for example 3 to 4 minutes. So 3 to 4 minutes every person will take. Okay. Now in that case, if there are 10%, then naturally the last person will be having some 40 minutes he has to wait. Okay. Say for example, if there are 15 persons are standing, in that case you see the number of minutes he has to wait. Okay. Now they complain. Now the manager wants to know whether to install a new ATM. Okay, increase the number of ATM, whether they put a new ATM. In that case, when you want to put a new ATM, because you know ATM, putting a new ATM involves money. You have to buy the machines, you have to get the infrastructure, air conditioning, all those things are there. So there is some money involved. Okay, so whether that investment will really shorten the queue length. Okay, that's what the concern is. Whether the adding one more ATM will shorten queue length, or whether you have to add two. Suppose If not 1, then 2. Okay. Or optimal number. How many optimal number of ATMs I should open? So this is a decision that the branch manager has to take. Okay. And for this, he cannot experiment with an actual ATM. He cannot bring an actual ATM, put it and see how long the queue length takes, because that he cannot do, because the ATM is not there. Okay, the problem is you have to install a ATM. Okay, the ATM which is not there. Okay, so in that case, what you have to do? Okay, so in that case, you will go for a simulation. Okay, now when you are simulating, how will you simulate the queue length? How will you simulate the incoming rate of the customer arrival? So customers are arriving. Customers are arriving. Okay, how to simulate this customer arrival? Because customer arrival is a purely random process. Okay, again, in that case, how much time on average a customer takes at the ATM? That's again another distribution. Say somebody may take say 5 minutes, somebody may take 10 minutes. Okay, somebody may take even 1 minute. Say somebody may just go inside, find their balance, come out. Or somebody may go inside, they may try to deposit money. In that case, it will take some 6 to 7 minutes. Say sometimes a student may go in and he wants to pay the fees. Okay, in that case, that will take even more. That will take even more. So the service time takes from say just from say a few seconds to say 10 minutes. So now you have to find the average. What type of distribution is this? Okay, what sort of distribution is this? So in that case, when you are experimenting, you have to experiment this. You have to pick a random value from this distribution to simulate the service time. So this is service time. So service time has to be simulated, for which you have to draw a random number. You have to draw a random number. Similarly, customer arrival has to be simulated. That has to be how many customers per minute. Number of customers per minute. How many are arriving? So for that you have to simulate. Yeah, here again another random number you have to simulate. So this is a different distribution D1. This is another distribution D2. Is D1 equal to D2? Can you take random numbers from the same distribution? Yes? No. Because you know that customer arrival is a totally different pattern, whereas the service time of an ATM is a different pattern. So generally you know that the service time of an ATM will be a standard normal curve. Okay, the service time of an ATM will be normal curve, where norm mu will be some 5 minutes. That's the average time a particular service takes. But whereas the service may even take longer time or shorter time. So the distribution should follow a normal distribution. But whereas D1, which is a customer arrival, is a different one. It has to follow a different distribution, number of customers per minute, and I think you will know that it's called Poisson distribution. Okay, that is number of customers per minute. Sometimes you may want to model the inter-arrival time between customers. Say for example, customer 1 arrives, after some time customer 2 arrives, after some time customer 3 arrives, after some time customer 4 arrives. Now what is the time between arrivals, 2 arrivals? What is the time between arrivals? Okay, suppose I want to model that. Okay, I want to draw random numbers for time between arrivals. Okay, say first customer arrives at 10 a.m. When will the next customer come? After how many seconds or after how many minutes? So that if you want to model, then we have to go for a distribution called negative, that is negative exponential distribution. negative exponential distribution. So you see in real life, okay, in real life, so there are different types of distributions for different types of processes. Okay, so to simulate such processes, you should draw random numbers from those appropriate distributions. Then only your simulation will be like real life. Otherwise, your simulation will not be real life. It will not be effective. Okay. So that is what actually we are talking about. And so I have mentioned some few distributions. So what is the distribution? Poisson, negative exponential, your normal. So I have mentioned three. So apart from that, I think if you remember, there are some more distributions which are there in our nature. For example, if you take a metal, cooling of metal and annealing of metals. Okay, you know what is annealing? Okay, so annealing means, say for example, you are taking an iron, you are heating it to say very high temperature, then you are allowing it to cool down. Okay, and you know that you want to make the iron strong. You want to make, for example, you want to forge it into a wheel of a railway or track of a railway, train tracks or wheels of trains. So those irons, they are not casted irons, they are actually forged irons. You heat them, you forge them, then you cool them in a controlled manner. Only then you get the strength. Otherwise, what will happen? The wheel will break because the metals are brittle. Okay, metals are brittle. So to make the metal strong, what you have to do is you have to apply some annealing process. We call it annealing process. That means you have to control the rate of temperature. You have to control the rate of temperature, the cooling rate, or I'll say control the cooling rate. Say after you have forged the metal into a wheel, you have to control the cooling rate. Then only the what happens, the wheel will become strong. Okay. Otherwise, the wheel will become brittle. If you suddenly cool it, it will become brittle. Okay. So in that case, what you have to do? Okay. So you have to, there is the algorithm in our computer science. We call it simulated annealing. So that says the same thing. That is, so if you take a metal and anneal the metal, okay, then it follows certain distribution, and that distribution is called the Boltzmann distribution. Okay, Boltzmann distribution. So you have to suppose the annealing of metals, they follow Boltzmann distribution. Then if you want to simulate annealing on a computer, then you have to create a random number. You have to draw the random number from this Boltzmann distribution. You should, that is, you should generate random numbers from Boltzmann distribution. Okay, this is one thing. Another example I'll give you is about, say, you take power law. Okay. Suppose you take, you want to know how many influential persons are there in a society. Okay, how many influential persons are there? For example, if we take a Chennai has a population of say 1.2 crore. The population of Chennai is 1.2 crore. But among this 1.2 crore, how many people are really influential? How many people are really influential? So if you count the number of influential people, that will be very, very less. That will be say around say 20 to 30. So in a population of say 1.2 crore, there is only 20 to 30% who are really influential persons in the city. Okay. So, but when you take other, what about other persons? Other persons are very, very common persons. They are common persons. Okay. So in that case, what is that? What is this distribution? This distribution is called the power law distribution. So it has it looks like this. So you have, say this is influential, this is your population. Then people who are very influential are very, very less. The curve will be something like this. So that means people who are influential, they are very less. But the people who are not influential, they are very more. Okay. So that is called power law distribution. Power law distribution. Power law means, so these are actually happens naturally in our what do you call society or a physical process, okay, or any other random process that happens in our society. So now suppose you want to really want to simulate these things. Now if you are really if you really want to simulate such things, then we should bother about distribution. Okay, and in that connection we are going to talk about variance distribution. Okay, so the best example is the first one is uniform distribution. That means you generate a random numbers from 0 to 1. You generate random numbers from 0 to 1. You divide that 0 to 1 into 10 bins. So each of size 0.1, 0.1, 0.2, 0.3, 0.4. So the width of this is 0.1. Okay, and generate random number. And if each bin contains almost same number of random numbers, not exactly equal, but almost same. Okay, then such random numbers are called uniform distribution. It's called uniform. Because the randomness is distributed. The randomness is distributed across the entire range of the numbers what you are generating. Okay, so this is very simple. Okay, simplest distribution is uniform distribution. I generate 10 numbers and my numbers are equally spaced or equally distributed in several ranges. Okay, so if that is the case, that is the easiest way of generating a random number. And most of our applications, they generate such random numbers. Okay, right. So uniform distribution. So I need not go much deep into it. Okay, so just know. Then another thing is about discrete and continuous distribution. Okay, so say you can have in physical process, in physical phenomena, the temperature is a continuous quantity. Okay, continuous, because temperature is not a discrete quantity, it is continuous. So in that case, a real annealing of metal will be a continuous process. It will follow a continuous distribution. But if the same annealing process, if you are going to do it on a computer, computer is not is a digital device, it is a discrete device. So here the time is not going to be continuous, it is going to be in step. So then the step is not continuous, therefore it is discrete. So then we can say it is a discrete distribution. So a process in nature, they are continuous, but when the same process, if you are imitating that on a computer, then the process becomes discrete. Okay, so we have discrete versus continuous distribution. So one example I have given you is the temperature. So temperature, if you see on a digital thermometer, it will say 28 degrees centigrade and suddenly it will say 29 degrees centigrade. But if you see a column of mercury rising and coming down with the temperature, then you find that the rise and fall of mercury is not in discrete steps, it is in a continuous step. Okay, so that's how the difference is between a discrete what you call distribution and continuous distribution. Now coming to the probability mass, there's another thing that you have to keep in mind, that the probability mass function and probability density function. Okay. Now say for example, you know the shape of the distribution. For example, I'll show you the standard distribution. This is x minus x mu. Okay. Now suppose that you want to know what is the probability that your x is equal to some value small x. This is small x. What is the probability that your random variable x gets a value small x? In that case, you want to compute this. Now, if it is a continuous distribution, continuous, it is like this. In that case, what you have to do? You have to add, you have to integrate this area under this thing up to this point. So this is nothing but probability of x less than or equal to small, less than or equal to small. So what you have to do is you have to simply from minus infinity you have to take, okay, to x, okay, you have to sum. So what you have to do, you have to integrate from minus infinity to x, p of x. What is this p of x? The p of x is nothing but your probability density function. Why I say probability density function? Because it is continuous. For a continuous data, we call it probability density function. If it is not continuous, if you are doing it on a computer, then what you will have histogram like this. You may have histogram. When you look at it, when you look at the top, it looks like this, but actually it is not so. It is a set of histograms. Okay. Now in this case, suppose I want to find the probability up to this point. Okay. Here I cannot go up to infinity. It will be naturally some value here and some value here. Okay. Now what I have to do is this value, say for example x naught. I want to find what is the probability that x is equal to some small value x1. This is x1. Now what should I do? I should integrate. I cannot integrate because this is not a continuous function. It is a discrete function. So I have to sum. Sum I is equal to x0 to x1. Okay, p of xi. So take the sum. You have to take each point like this. Compute the p of I. This is p of I at that particular point, and just add them. Okay, and that gives you the probability of x less than or equal to some x1. This is equal to this. Okay. So now you see that in a discrete case, you have to do a summation of the probability. This is not probability density function, but it's probability mass function. PMF. We call it probability mass function. So if it is a discrete case, we call it probability mass function. If it is a continuous case, we call it a probability density function. Okay. So now this is normal distribution. Normal distribution in continuous case. And this is the same normal distribution in discrete. So here you see that this may not be 0. It will extend up to infinity. On both sides, this will go up to plus infinity and this will go up to minus infinity. But here in real case, it is not so. At this point it will end, at this point it will end. Okay. Now you see that this is the difference between this is a probability density function, this is the probability mass function. Okay. Right. Now you have to understand this. Now how will you generate this? How will you generate this? Because we need probability from such generation. So for that you can use this particular formula. This formula is given here. Box-Muller-Gauss method for normal distribution. So you can use using uniform random. Here I can generate always a uniform random number. E is a uniform random number. So generating uniform random number is not a problem. Generating uniform random number is a problem because we have seen an algorithm. So using that uniform random number algorithm, we can generate a random number from a standard distribution. Okay. So that's what the thing is. Okay. Now this is negative exponential distribution, I told you, no? So I was already mentioned about this negative exponential distribution. I mentioned about this is in interval. Say for example, if you want to measure the time between arrivals, time between events. What is the time between events? If I want to model this time between events, then the time between events is taken care of by this negative exponential distribution, and this is a positive negative exponential distribution. And sorry, so there are two things. Just yeah, this one. I think I skipped one. Yeah. So this is on the positive side. Okay, when x is greater than 0 or t. In this case, I have put as t, and this is the negative side when t is less than 0. T is less than 0. When t is less than 0, what is the, how does the curve look like? And when t is greater than 0, how does the curve look like? So that's what we are. And for generating them also, you can generate using this formula. I can generate using this formula, where rand is nothing but a uniform random number in this 0 to 1. So generating a uniform random number between 0 to 1 is easy. It can be done easily, but doing it on a generating a random number from a distribution is little difficult. Okay, so that's what I mentioned. Okay, now next we'll take a small. I think yeah, I think we are nearing 4. So I just introduce you this concept of what is a random walk. Okay, and I think with this we will close today's session. So a random walk, okay, is something that is again a random process. Okay, so here I will give some examples. Okay, like for example, you have a grid. Okay, so this is a grid. Okay, where the green ones are trees in a forest. So this is the area of a forest. Okay, this is an area of a forest where the green ones are leaves. Sorry, trees which are in the forest, and the red ones are the burning trees. The trees are burning due to forest fire. You know that forest fire is a common phenomenon that occurs in every place, anyway, whether India or abroad. So in summer you will find that somehow by accident fire is generated and the entire fire spreads in the forest and it destroys the complete forest. Okay. Now you want to simulate how a forest fire works. Okay. How does a forest fire move? Okay. So for that we are using this method, which is called the it is called the random walk cellular automata. It is called the random walk cellular automata. That means that and what about the this gray one? They are ash, and white the empty space. So this is the meaning of different colors in the graph. Now you see that you start with a particular configuration and you want to say that this point the fire starts. So how the fire will spread? Okay, throughout the forest. That means if you have a cell like this, if this cell is on fire, how it will spread to this side or this side or this side or this side. So fire can spread in all directions. So what is the probability that the fire will spread up, down, east, west? So you have to tell the probability. Based on that probability, the fire which is now burning here will go to the next here, burn that. From that, again you have to take the neighbor and another neighbor you have to find what is the probability that it will burn. So like that I can simulate. You see that's how it is getting simulated here. And when you see that, you find that ultimately you will see that not the entire forest is not lost. Just observe the trees that are burning. Once a tree is burned, it no longer burns because it becomes ash. Okay. Similarly, empty spaces they do not burn. because empty spaces, there's no, they don't have anything. So who can burn? A tree which is nearest. There is only a green node near to your node will be caught in fire, not the all the nodes. Okay. So this is what actually you have to keep in mind. So this is where we use the technology of random walk. The random walk means the fire can go this way, this way, this way, this way. Okay, just for only thing is that you have to give a probability. What's the probability of going towards north, south, east, west? But actually, if you take forest fire, it will also depend upon the wind. Suppose if the wind is in a particular direction, if the wind is blowing towards north, then the fire will spread towards north more. Okay, fire will spread towards north more. If the wind is blowing towards east, then the east will be, fire will be spreading fast along the east direction. Okay, but if you assume that there are no such problems of what you call no such problem of spreading of direction. Okay, like there's no wind, it is not a windy day. Okay, so something like that if you assume, then in that case the fire may go from one place to another place purely on a random basis. Okay, so purely on a random basis, in that case you will find that the fire is actually moving in a random manner. So I will also give you some examples. Suppose you have a glass of water, pure water, a beaker of water. In that you drop one drop of ink. You just drop one drop of ink. Now, how do the ink molecules, they disperse inside the box, inside the beaker? That is a purely random walk procedure. So each molecule, by virtue of its thermal agitation, will go from one place to another place inside the liquid. Initially, you find that it is more concentrated on the top, but ultimately, if you wait for a long time, you find that the entire liquid is blue. Okay, entire liquid is blue. That means the ink has spread in all the directions. Okay, so this is what actually you have to keep in mind. Right. So this is just an algorithm. So I don't take this. So once what we do generally is we take so many. What we do is we never conduct an experiment by conducting a random experiment once. You have to conduct the random experiment n number of times, and after that you have to take, for those n number of times, you have to take the average. That's what generally we do. And each average is what is plotted here. Once you are doing it for some time, then you will find that there's a beautiful relation you can find. Here you can find the relation between the step size. For example, random walk, what is the step size and what is the distance covered. So you know that when the step size of a random walk increases, the distance cover also increases. Okay. So this is again a random walk, is a pure random walk where you don't find, you say that an animal or a bird or whatever can move in all the directions equal probability. Okay, but sometimes it may not be true. For example, if you take the case of say some hunting procedure, generally you will find that the birds or animals, they will hunt in a particular region. They will hunt in a particular region, they will follow a random walk. Then after that, when the things are exhausted, they take a long distance leap, and then they do a random walk. Then they take a long to a random walk. Like this. So this is what is called Levy flight. Levy flight simulation. That means this is typical for hunting behavior of animals. Okay, they will never hunt in a particular place. They will be doing a random walk in a particular place for some time. After that, they will find that they don't find enough food here. They will take a long distance, and then they will do a local search here. Then again, they will take a long distance, do a local search here. Okay. So such distribution is called a Levy flight distribution. So I think today I have talked much about things like probability, starting from probability, So what is the probability, how it is useful to us, okay, where it is applied, okay, and how you can simulate a probability. You can simulate probability using random numbers generated from a distribution, okay. And we have seen what is the distribution is, what types of distributions are there, and different names for the distribution, and in nature and in your human life, real life, you find different distributions which follow different uh, uh, applications, okay, like Poisson distribution, negative exponential distribution, normal distribution, okay, Levy flight, Boltzmann, okay, power law distribution. So you see, we have seen so many distributions, okay. All these distributions are naturally available; they are occurring in nature, okay, and therefore to simulate such distributions, you have to really use what you call appropriate methods for simulation using this approach. Okay, right. So I think with this I can close my session today. If there are any questions, I can take questions. Otherwise, we can close. Okay. Any questions? And I think all of you who have studied computer science would have studied probability and statistics. It is always there. So this is an integral part of any computer science or IT course. So you see the importance. Okay, the importance is really there when we have to use it in simulation. Okay. System group, I think there is an echo. In system group, can we conclude?
Yes, sir.
Okay.
So, hope participants not having any doubts, sir. On
Okay.
behalf of myself and all participants, I would like to thank Dr. R. Thangarajan, Professor and Head Department of Information Technology, KEC, for providing the depth knowledge in the probability. Hope this session gave the better perception for how the probability distribution really formulated for data-driven model for doing their research work, and also lay the foundations of mathematical concepts behind in probability. Thank you, sir.
Thank you so much. Thank you, madam, and thank you, participants, for your patient listening. Okay. So I think I have one more session after some time on interpreting machine models. Let me meet you then. Okay. Thank you so much.
So participants, kindly wait for a few minutes. I will be posting feedback link. There is problem in system group.